Hello, everyone. Welcome to today's webcast, part one of our Designer to Analyst series. I'm the moderator, Krista Prokos, and before we get started, I wanted to remind you that you can submit questions for today's presenter by typing them into the Q&A panel at any time. We'll collect them and address them at the end of the presentation. And now I'd like to introduce our presenter. We're happy to have with us today Sasi Sithambaram. Sasi is a Senior Technical Specialist and Manager at Dassault Systèmes SOLIDWORKS. Sasi, take it away.
Thanks, Krista. Can you hear me okay?
You sound great.
Great, thank you. As design is evolving, manufacturing is evolving, we are stepping into that industry renaissance, right? Or as we are calling it, engineering 4.0. Essentially, we are starting to change the way we are designing because we have access to more manufacturing methods, right? So a lot of new manufacturing methods have been introduced, such as additive manufacturing, 3D printing, metal printing. So with all these new technology and combining these new technology with VR and AR, we need to be prepared for this industry renaissance. So today's presentation is going to revolve around this new technology growth and how we at SolidWorks are preparing for this, specifically when it comes to validation and innovation and evaluation of your designs. So historically, we've done this using our simulation product suite. So some of you on our webcast today might already be users of SolidWorks simulation, our plastic simulation, our CFD analysis, which is flow simulation. And as of last week, we released another new technology, which is simulation engineer, which we're going to talk about tomorrow. So as we are evolving, we are starting to add more tools to these product suite to give you the ability or to allow you to be prepared for this change in the marketplace. So I'm going to focus on some of the new technology that we introduced in our product suite, as well as a continuation for tomorrow, I'm going to talk about new technology that we introduced. So quickly, for today's agenda, we're going to talk about integrating next generation technology in your design flow. Of course, that involves additive manufacturing overview. In today, engineering companies are in one way or another using additive manufacturing. So we wanted to cover that and talk a little bit about how SolidWorks is preparing for that and have integrated tools today to help you with designing and validating and producing 3D printed parts. So we'll cover additive manufacturing, topology optimization, generative design, and our 3D experience marketplace as well. So the first part of this presentation, we'll talk about additive manufacturing overview. So rethinking traditional manufacturing. So we've always relied on our traditional manufacturing methods, whether it's CNC, milling, and our designs have really followed the rules and regulations of this traditional manufacturing. But today we can start to rethink manufacturing because 3D printing gives us much more design freedom. When it comes to 3D printing and additive manufacturing, it's really a driving technology and driving factor of that Industry 4.0. In this chart, we can see specifically where additive manufacturing is growing exponentially. So we can see specifically in prototyping and product development, and of course, innovation. Now, the reason for this is kind of going back to the design freedom, being able to test and innovate outside the box of our traditional manufacturing methods. Our product don't have to be as linear as what it used to be. It can be more organic, and it can really fit the requirements that we have, as opposed to massaging the requirements to be able to fit the manufacturing methods. So with these types of technology, right? So this is 3D printing and softwares that go with it. Um, 3D printing is everywhere today. It's readily available. If you think about 10, 15 years ago, only large corporations had access to this. Today, everyone has access to this. There's hobbyists that even have 3D printers at home. So why additive manufacturing has grown so much over the last few years? So these two charts really show why and how. So in terms of part complexity, we are able to design more complex parts. So for example, these bone structures, which are minimum mass components, but still able to retain quite a bit of strength integrity. These are typically 3D printed parts and are you really can't machine them using conventional methods. Another area we've seen the growth of additive manufacturing is when it comes to low production runs. So in the past, if you had a low production run, it might not be cost effective to cut a mold and use injection molding. So when you have a short production run of 100 parts, 1,000 parts, 3D printing starts to make a lot of sense cost-wise. So there is a break-even point where at some point additive manufacturing might not be so much cost-effective anymore, and at that point you can jump to other technology that's always been around, the traditional manufacturing methods such as stamping or CNC or injection molding. So design for additive manufacturing, like I said, it gives us a lot more design freedom, so we can start to look at lattice structures and really design to fit the requirements that are given to us. So if we think about historically how we've designed in the past, is we've looked at our requirements and then we think about how parts have to be manufactured. Now we can actually send the manufacturing thought towards the back end of that design process, because 3D printing allows us quite a bit of flexibility in that area. What about part consolidation? So we've started to see large corporations integrating 3D printing technology into their everyday production. So GE is a very big proponent of that. GE has invested a lot of money into growing 3D printing technology. And the reason why is because they are already integrating 3D printed parts into their assembly designs. And they are starting to see a huge cost savings in that. And having this 3D printing technology and additive manufacturing technology continue to grow will only benefit them. So, with all this talk about design freedom, is it can we just design whatever we want when it comes to 3D printing technology? Well, unfortunately not. When it comes to 3D printed parts, we still have to consider things like supports, the possibility of shrinkage, warpage, how our holes are being positioned and designed, what our minimum wall thicknesses are, because it's being driven by the specifications of our 3D printers. So with all these questions, we need to be able to validate our designs and also ensure that the design, the model, the CAD model that we're sending to the 3D printers are the best model that is for the 3D printer that you have chosen for that manufacturing run. So just a quick overview: no tooling required, faster to market, manufacture the impossible. So with that said, what are some of the best practices for 3D printing using SolidWorks? Today we have a number of tools to help you design better 3D printed parts. So one of these tools is Print 3D, which allows you to take your CAD model directly from SolidWorks to your 3D printer. It runs a thickness analysis for you, decides the orientation so you can check for support surfaces. Because the way 3D printers work and it builds the part layer by layer, we need to ensure that it is supported properly. And you can uh, export the CAD model directly as an STL, AMF, or 3MF from SolidWorks directly to your 3D printer of choice. Another tool that is heavily used for 3D printed parts is our thread wizard, which allows you to set up your tap and die and using inserts, and you can consider some different threads. Now that these threads are 3D printed, you can start to customize these threads, possibly even change the pitch, change the number of threads that are involved to meet your requirements, shorten the thread length, and you can do all of these using our thread wizard. Printing assemblies. So using our clearance verification, you have to make sure that there is some gap because in a lot of cases, being that we are SolidWorks users, we always design to fit, and we add our tolerances, our clearances to our drawings. However, if you plan to send your CAD model directly from SolidWorks to your 3D printer, we have to add some clearances so that the parts will stay separate when it's printed together, and we can do that using our clearance verification. So here are just some tips and tricks about designing a part for 3D printers. This is something that I just learned recently myself, that having your features unsupported actually can almost double your 3D printed time. So adding a quick fillet of chamfer can really reduce the number of how long it takes to print your components. So control destiny of printed parts using SolidWorks, the tools that are already integrated with SolidWorks. It's available in every version of SolidWorks. So if you're using SolidWorks today, you already have access to all of these that I showed. Identify, fix issues up front, optimize 3D print time. So the next thing I wanted to talk about today is topology optimization. So topology optimization is a tool that we introduced as of SolidWorks 2018. This tool, this new tool, which falls under the generative design bucket, goes hand in hand with topology optimization. Today, when we talk about design, we've always advocated that you want to continuously validate your design from the initial design stage and make design changes, make your revisions based on those results. And this is called a parametric optimization. So you come up with an initial design based on your perhaps your customer requirements, and you run your design validation, whether it's linear static analysis, your drop test, your buckling analysis, and depending on the results, you perhaps will thicken a wall, maybe you will add some ribs, maybe you will change the material, and will go in a cycle until you get to the final design that 100% meets the requirement that you feel is the best design from that initial design. What we are proposing today, or today is parametric, or what we're proposing in the future is, can we design the best part from the get-go, from the initial design, right? So in the past, what we've seen is, although we've made design changes and revisions based on validation results, the final design always has or always retains some form or shape of that initial design. But what if you can completely change that initial design so that you have the best design from the beginning, and running design validation after that point is more of a confirmation, and you're able to make small changes to get not just the best part, but the fully optimized design. How design approach to maximize return of investment for additive manufacturing. So a lot of times we talk about minimum material. Now, minimum material is a big area, big aspect of 3D printing. If you think about CNC, the more material we remove, the higher the cost. So while it might be lighter, the cost to continuously cut holes in a CNC part might make that not a viable option. But with 3D printing, it doesn't matter how many holes you include in your design. It's always going to take about the same. It's always going to be about the same cost, and it's always going to take about the same amount of time. So it's always a good idea to try to minimize the mass as much as possible. So we want to design the build, not just the part. So generative design in SolidWorks is available as part of our simulation professional. And you can see to the right of the screen as there's a quick introduction as to how this tool works. So by setting up your loads, your typical simulation constraints and loads, and include your goals such as minimum mass and adding manufacturing processes or controls, it will generate a design for you. So let's go ahead and take a look at an example from idea all the way to final design to kind of illustrate that process a little bit more. So here is a napkin sketch of a payload mount, and essentially we've gotten a request from perhaps a customer, and they've given us a few requirements. So we usually start with a quick sketch just to get that idea out before we jump into SolidWorks and start designing the part. Here we have a very simple design that most of us that are using SolidWorks today are used to, right? We're using very simple features such as extrude, chamfer, cut extrude to design this part. So this is the typical design that we've always come up with. Now, using this initial design, we're going to use topology optimization and take advantage of this generative design tool and see if we can generate a better initial design. So here we have a initial strength validation of our component, and this is always a good idea to run a validation design to fully understand how the forces are being distributed on your component so that we can include any critical components into our initial design before we run that topology optimization. The reason for this is because as the topology optimization removes and redistributes material, we want to ensure the software will retain any critical features. So as you've seen in the last image, we fixed the 4 holes on the 4 corners of this payload mount. And here we are adding forces to the top of this mount. So this is part of a drone. It's a flying object. So your roll pitch force load is very important for any aviation products, any product that flies. So once we have that in place, we can run our initial strength validation to see the distribution of stresses as well as our factor of safety and displacement. So obviously, because of how thick this component is, our factor of safety is very high. It's 36, but this is a good thing. We are giving the software as much material as possible to work with as it removes and redistributes the material for the newly generated design using topology study. Once we have the initial analysis, our initial linear static analysis, we can step into our topology optimization And the first step to that is setting our goal. Now, within SolidWorks simulation, there's three goals that we can set: best stiffness to weight ratio, minimizing maximum displacement, and minimizing mass with displacement constraint. Now, while minimizing displacement might be a major criteria for you, it's always a good idea to start your first revision, your first analysis with the best stiffness to weight ratio, which is why we have a default in parentheses right beside that goal. This initial goal will allow you to remove the maximum material while still keeping the best stiffness within that component and keeping it within an acceptable factor of safety that you can set as well. So setting this this goal and constraint with best stiffness to weight ratio and setting the maximum mass that you would like to reduce. So in this case, we can see that here there's a 90 in here. So it's not necessarily the software will remove up to 90%, but it will attempt to remove up to 90%. Now, once we've set our goals and constraints, the next thing that we want to do is set up our manufacturing constraints. So here's where you will really drive this analysis and drive the final shape of the component. So depending on how this part is going to be manufactured, you can add manufacturing constraints such as adding preserved regions. So as I mentioned, if you have any critical features such as the mounting holes for that payload mount, as I shown earlier, you can select those and say these faces need to be preserved. You can also control thickness. So, for example, if your component has to have a minimum thickness or a maximum thickness, you can add that as a control. You can add demo directions if this part is going to be stamped or injection molded. And last but not least, if you have a symmetry component, you can remove half the component and simply run the analysis on one half. This is a time-saving technique that gives you results quickly, and it mirrors the results over to give you the maximum material removal. So here we are setting up manufacturing controls to preserve that the four mounts on four corners, as well as the loading area on the top. And running the analysis, this is the result that was generated. So this is a very unique design that perhaps no one might have thought of, but the software helped us generate this initial design, and it removed as much material as it possibly could. And while it attempted to remove up to 90%, you can control how much material you want to remove based on the results. So this slider right here, which says heavy to light, as you move this slider, it will remove as much material as it could, and it will keep as much material as it could. So depending on the results that you get, if the walls were too thin or the generated final design perhaps is not aesthetically pleasing, you can add material back to the model simply by moving that slider. Once you're happy with that shape, you can export the model as either a graphics body to use as a template to design over, or you can even export it as a solid body or a surface body. So in this case, we went ahead and imported the generated design or the optimized design as a solid body. Now this is SolidWorks geometry. So using our SolidWorks tools, we can actually design over this, and all of these faces, edges, holes are all selectable geometry. So using SolidWorks, we were able to design this component, which is 100% parametrically driven. And if you remember that process, we come up with that initial design, and before we finalize the design, the one step that we need to the next step is to confirm or validate that design. So again, we run that stress validation, and we can see here the von Mises, and this is a really good comparison as well. We can compare the stress distribution, the displacement, and even the factor of safety to that initial chunky design that we had. So here you can see that our factor of safety went from 36 down to 15. While there was a significant drop, we're still in a very healthy margin for a factor of safety. So to summarize what we've just seen, topology optimization is a great way to create lightweight designs, and it's a great guide for additive manufacturing components. So what else? Once we've run our design, we've validated our design, we've confirmed that this component has the best stiffness to weight ratio, what else should we be concerned about? Well, I would be concerned about how this part would perform in operation. So depending on the application of the component, we can run additional tests. So for example, here in this component, this is a component that's flying in the air. So there might be some vibration issues. And it's also we could categorize this as a hobbyist component that might be used by children. So potentially dropping to the ground. It is a drone, so it could potentially run out of battery, and it could fall to the ground. And we need to be prepared for if those things happen. So let's take a look at what other analysis we can run in this for this specific model. So like I said, there are many other types of analysis that can be run depending on your application, whether it's frequency, fatigue, buckling, or thermal analysis, or even testing out new materials. So here we ran a frequency analysis within SolidWorks simulation on the original design, and we were able to generate 10 mode shapes. And looking at the different mode shapes and the different operating frequencies, we want to try to avoid resonance. So using a PSD input, we can run a random vibration analysis. And here we can look at a spike of our acceleration at right around 1200 hertz. So the goal here is to try to avoid any operational frequency at right around 1200 hertz to avoid resonance. And this can be done using many different methods, such as changing the design, changing the speed of the motor, or even perhaps changing material. And you can evaluate all these different changes within SolidWorks simulation. As you are making these changes, you can rerun the analysis to see where the spikes in that acceleration is changing, or where it has shifted to in the for the frequency. So we can also recreate a harmonic analysis, or as we call it, a shaker table. So some of you might be familiar with this. If you have components that are vibrating, a lot of times for physical prototyping, you'll put it on a shaker table so we can recreate that virtually in the analysis. And here we can see two spikes, again right around 1200 hertz, and another spike at right around 1800 hertz as well. So what about product life? So we talked about vibration. We've identified some operating frequencies that we have to avoid. Now let's address product life and perhaps abuse. And if this product is going to be sold, what type of warranty can you provide with these types of components? So using our fatigue analysis, we can cycle our analysis by a number of times. So whether it's 1,000 cycles, 10,000 cycles. So if you think about it logically, if we provide a 1 year warranty for this component, and we assume that it's going to be used 365 days a year, and it could potentially fall 10 times a day. So that is 3,650 cycles that we can test this for. And if you add a factor of safety, then maybe we can say, let's test this for 10,000 cycles. And if it passes 10,000 cycles, then we can warranty this component for 1 year. So running the fatigue analysis, and for this we ran it for 10,000 cycles. We can see areas that will fail long before that 1,000 cycles. So it's kind of given that mounting, where it's mounted, as well as where the load is being applied, it could potentially fail right around 2,900 cycles. So again, if you're hoping for this component to withstand 10,000 cycles, then is this are we required to change this component? Are we required to use a more stronger material? What about at operating frequency of 600 hertz? So when it comes to fatigue analysis, we can include frequency as well as, when it comes to fatigue analysis, we can include frequency as well as static analysis as a combination, as a multi-load analysis to see if it will be able to withstand how many number of cycles it would be able to withstand. So you can see here this number actually went down a little bit to now 2,800 cycles, or actually 288 cycles. So that's relatively low. So addressing failure mode, identify potential areas of concern, ensure product performance, and it paints a complete picture of how this component is going to be used, and it will have its strength, integrity, and how it will be able to withstand operational use. So I wanted to wrap up the presentation today with our 3D Experience Marketplace. So 3D printer user statistics. So as I started this presentation today, I talked about how a lot of engineering companies today are using 3D printer in some capacity, whether it is being outsourced, whether you have a 3D printer in your facility, or you are working with a company that is using 3D printer technology, or testing their prototypes using 3D printers. It is in some capacity being used, and this usage is only going to keep growing. So why do people outsource 3D printers? Well, maybe investing in a 3D printer is not in the budget right now. Maybe perhaps the amount of cycles or production cycles you have doesn't warrant for a 3D printer. So there could be many different reasons as to why you would outsource a 3D printing or 3D printed parts. As we know, that is a typical typical process when it comes to your design of these organic shapes. We've introduced 3D Marketplace as part of SolidWorks. So this is something that you can access directly within SolidWorks. You just need to turn it on as an add-in. And essentially what this does is it connects you with 3D printers, suppliers, well, not 3D printer suppliers, but machine shops, manufacturing vendors all around the country all around the world actually that can 3D print components for you. So if this is a space that you would like to get into, but you're not ready to make that full investment, this is a natural progression. So you can outsource these components right now to see how it works, how you can integrate it into your design process, and then once you've seen that cost benefit, then you can get in touch with companies like Fisher Unitech to look at your possibility of bringing a 3D printer into your facility, and they can facilitate that process for you. So to wrap this up, I'm just going to play a quick video. This will give you a really good idea of what 3D Experience Marketplace has to offer, and then we can wrap this up with some Q&A. So here is the final part that we went ahead and 3D printed using the 3D Experience Marketplace. So again, we're not a big manufacturing facility. We're more of a hobbyist, and we just use um, the uh, the services of 3D Experience Marketplace to help us manufacture that part. So identifying the best partners for every project, go straight from design to parts, digitize your collaboration process so it goes directly from your SolidWorks 3D CAD interface directly to the vendors, reduce errors and risk because there's less hands on it, ensure traceability for your business. So to wrap up, reduce errors and risks, go from design to parts, ensure tighter collaboration. So for today, what we've seen as part of the example, we've talked about linear static analysis, we talked about fatigue analysis, topology optimization, and a secondary analysis where we ran frequency, harmonic analysis, and random vibration. So you can see the breakdown of all the different tools and the different simulation products that carry those tools. As a continuation to today's presentation, we're going to have a part two of this presentation tomorrow. And just to give you a little bit of teaser, we're going to talk about some additional technology, high-end technology, which is our Simulia SSE, which is Simulia Simulation Structural Engineer, which is a new product that we released as of a couple weeks ago. And here are some examples of the analysis that we can solve with that. And we're also going to talk about how we can collaborate between mechanical, electrical, and electronic designs using the simulation tools within SolidWorks. So taking your electronic designs, running simulation, and changing those PCB designs based on simulation results.